So how do I now find the profiles? I need to distinguish the different modes. So how do they look like, right? So what do? I know the values here for the core and the cladding. This is the, remember we started with r as a function of r and phi as a function of phi, and we found out r and we found out phi. Now what are the variables here? A is a constant, I do not know yet, but u is, now I know u is equal to, what was, how did we define u, you remember? Square root of beta square minus k naught square n1 square, or is it k naught square n1 square minus beta square? K naught square n1 square minus beta square. And beta I know. How do I know beta? Because for each mode I know what is the value of b, and from that value of b I know what the value of beta. So I exactly know u, which is a number now. Okay, u is just a number depending on which mode I am solving. A is also a number. R is the only variable. So I can now find out the Bessel function for that specific argument and plot that. And of course I have cos L phi, sin L phi, both solutions. So for each value of L I can find out what are those m solutions, find out the b's for those m solutions. From those b's I calculate u for those m solutions and then substitute here and find out. I can repeat it for all values of L. Okay. Similarly I can do for the cladding. Now A is a constant which I do not know, and I really do not bother to know about A, simply because if I want to know, what do? I say that my power that I am launching at the input is now, depending on how I am launching, is distributed between the different modes, and that A is telling you what fraction of power is distributed in different modes. So I can just do a normalized plot for finding out the fields. So this is something that we have a code which solves not through this V versus B and so on. We can actually do a solution using a finite difference method also. The electromagnetic wave equation can be solved. So we have solved it for n equal to core is 1.45, cladding is 1.444. So it's a slightly larger difference between the core cladding, so that the V number is 5.34, right, because N1 N2 is slightly having a larger difference, and it turns out that at 1550 nanometer these are the modes supported. Okay, these are the corresponding values of beta. I mean from the B you can find out what the betas are and the corresponding n effectives are. So you see the 1.4495 is 4495 is close to the core, that is for the fundamental mode. 4473, this is 4440. The next mode would have been something less than 4440, which would have been discarded. Okay. Now you know the n effective, or you know the beta, and from that you can, using the method that we discussed earlier, we can find out the profiles. This is how the field profile looks like. This is not elliptical actually, this is circular, it is just that the figure got a bit stretched here. The LP01 looks like a circle, and it has the intensity is obtained by just doing a mod square of the field, and because you have a field it has a face in it. For example, in LP11 mode you could actually have this is only one solution. Can you tell me whether this is corresponding to, see LP01 was only degenerate by 1, right, there is no L equal to 0, so there is no cos L phi sin L phi solution, so there is only one possible mode. Whereas for LP11 you can have cos phi and sin phi. So which solution is plotted here? It's a cos phi solution or a sin phi solution. If this is my phi equal to 0 angle, then what is plotted here is a sin phi solution. How would the cos phi solution look like? This whole thing turned 90 degree. Okay. Correspondingly this. So this blue and the red, if you look at it, blue means negative values of field, red means positive values of field. What does it mean? If I take a profile across this, it is going to look like, and then this is 0, and this should be positive. It just simply means that the phase shifted, right? It's a phase shifted version. The two lobes have different phases. One is negative field, the other one is positive field. But if you do mod square, that phase disappears, which is why you have the two lobes intensity distribution. If I plot it, it is going to look like this, right? Similarly, you can have LP21. So L equal to 2, which means you have cos 2L phi and cos 2 phi and sin 2 phi solutions. Which one is plotted here, cos 2 phi or sin 2 phi? At phi equal to 0, you have something. So cos function is plotted here. Okay. And what would the corresponding sine solution look like? I mean, the propagation constant will be the same, but the field solution is going to look turned around. So instead of this, you will have something like, this. This would correspond to the sin phi solution, sin 2 phi solution. Okay. And LP02 is looking like this. It has maximum here. So again, L equal to 0. L equal to 0 means that there is no zeros in the azimuthal direction, but it actually starts getting 0 in the radial direction, which means that the modal profile, if I plot, it's going to look like maxima and then 0 and then one more maxima and then one more maxima. That's how it's going to look like. Larger values of L will give me more number of zeros. This again probably cos phi is plotted, sin phi is plotted, and similarly higher order modes. Okay. So in general, you could have 2L zeros in the azimuthal direction, m minus 1 zeros in the radial direction. Why 2L zeros in the azimuthal direction? For instance, you take L equal to 2, you have first 0, second 0, third 0 and fourth 0 in the azimuthal direction. In the radial direction, there are no zeros, right? I did not get a profile like this. I did not get a profile like this. For instance, here I got a 0 in the radial direction. I got maximum, minimum, maximum. So in along the radius, I have a 0 here, and that happened when L equal to 0, m is equal to 2. So you say 2L zeros in the azimuthal direction, m minus 1 zeros in the radial direction. This is how you will identify. So you had a question how to identify these modes. So find the number of zeros in the azimuthal direction, number of zeros in the radial direction. Of course, you can't count, for instance, this as a 0. When I say 0 in the radial direction, there should be a 0 between two maxima. Okay. For example, here LP12. So where are the 2L zeros? One 0 is here and the other 0 is here. And where are the two m minus 1? So in this direction, as you look in the radial direction, you could have one minimum here and again a maximum is appearing, right? So that's how you can identify the field profile. But of course, one thing you have to understand is that you can get this field profile in an experiment only if you launch that specific mode. Otherwise, what is the profile you will get? If I launch all the modes together, I will get a superposition of all these, a mixture of all this. And then from that, I should be able to extract what is the ratio or what is the proportion of each modes. Okay. Now the question is, what is the velocity of each mode? How do I find the velocity of each mode? I know what is the n effective of each mode. So the velocity is going to be c over n effective. So each mode is propagating with different velocity. Which mode is the slowest? Which mode is the fastest? Is the fundamental mode slowest or fastest? Then you should also remember degeneracy in terms of polarizations. Each mode can be supported in two polarizations. So if I launch an LP01 mode, I could have an LP01 X and LP01 in the Y direction. Okay. If I launch an LP11 mode, this corresponds to sin phi solution, this corresponds to cos phi solution. So, there is a degeneracy because of L, and each of that could be in X polarization or it could be in Y polarization. So, how many degenerate modes are there corresponding to LP11? You could call one of them as LP11A in the X polarization. You could call this as LP11B in the X polarization. You could call this as LP11A in the Y polarization corresponding to the sin phi solution, and you could call this as LP11B in the Y polarization. And this you can call it as LP01 in the X polarization, LP01 in the Y polarization. Now, one of the things we were talking about in the beginning of the course is to improve the spectral efficiency, right. We said we went to 16 QAM and PAM and multiple modulation formats to improve the spectral efficiency. A recent trend is also to improve the spectral efficiency by launching light in two polarizations. So, that is what we gave us the polarization multiplexed transmission. So, we transmitted LP01 in the X polarization, LP01 in the Y polarization. The next trend is also to use a slightly multimode fiber, a fiber that supports only fundamental and the higher order mode. So, the V number is between 2.4 and not really 4, the next higher order mode, whatever was a number slightly less than 4 actually, right. So, increase the core area slightly so that the fiber supports the fundamental and the next higher order mode, and then if you launch your information in all the three of these modes, where are the three modes coming here? LP01 and the two degenerate modes, LP11A and LP11B. How many fold increase in spectral efficiency will you get? LP11 itself corresponds to 4 degenerate modes. So, I can in principle launch in X polarization in 11A, X polarization in 11B, Y polarization in 11A, Y polarization in 1B. So, I can launch independent set of data in each of these 6 modes. Think about it as 6 pathways inside the fiber, right, and then increase my spectral efficiency by a factor of 6. What is the disadvantage? Of course, your fiber has to change. It has to be slightly multimoded. Wavelength you cannot change because 1550 is a standard wavelength. And the other big disadvantage is that these modes will start mixing with each other. So, the receiver, even though you send independent set of information, in the receiver all of them will be mixed. But we make use of digital signal processing to extract the original components, provided the mixing is all a linear mixing. Understanding the modes is important, has become important because now we are doing what is called as mode division multiplexing. Mode division multiplexing is a scheme where you use multiple modes to transmit independent data. It is not yet commercial, there are no commercial standards on it, but this is where the research is going to. Very nice question. Are these modes orthogonal to each other? Yes, they are solutions of linear differential equation. So, and they are solutions, the power series solutions and Bessel function solutions are orthogonal, which means that if I do psi LP01 psi LP11A conjugate, I integrate over r dr d phi, I get an answer 0. If I do psi 0, if I do LP01 psi LP01 star r dr d phi, I should get 1. Similarly for each modes. So, they are all orthogonal set of modes, which is why we are able to transmit our information through these orthogonal channels. Okay. One last thing is that in the course we will be talking about fundamental mode, and the fundamental mode, even though it is represented by a Bessel function, for all practical purposes you can put it as a Gaussian. You can use a Gaussian function to represent that. Irrespective of the refractive index profile, so long as it is a step index profile, you can represent it as a Gaussian with e power minus r square by w square, where w is the spot size of the mode field pattern, which is this. A is 2w, the mode field diameter of the fiber. It turns out that for V between 0 to 2.5, which can happen for different wavelengths, there is this empirical relation given by originally by Marcuse, a person who had done a lot of experimental work with fiber optics. W by A is this relation. It's again an empirical relation, so don't ask me where these constants came from. You plotted W versus V and you found this fit, right. So, which means that for a given V you can find out what is the Gaussian profile, okay. And homework for you is this. It's important to do this homework, because then we will understand what is the difference between propagation through different wavelengths. It's the same fundamental mode, but they are different. The difference between that is what will come out if you do this homework. You have to find out what is the mode field diameter using Gaussian approximation. All right.